Hello, hello. How's everybody doing? I tell you what, it is a beautiful Monday out there. Not a cloud in the sky. Not too hot, not too cold. Just right. Definitely after class, I'm just gonna make some time to sit out there in the sunshine, maybe have a book, something like that. How are you guys doing this Monday? This little tomato plant behind me, wait, that way, in the window, it's slowly been growing. It's almost to like the top of the window now. And we don't have, usually for tomato plants, you have like a stake or something that the plant can grow along. And so the other day, Hannah walked in here and she noticed this whole thing was just flopped over, hanging on the ground. So what we did is we tied a string from the top of the plant up to that little bar up there. And that's how the plant is staying upright. Isn't that just fantastic? Isn't that the most ingenious thing you've ever heard of? All right. I'm guessing you don't have a green thumb. You could say that. You could say that. Hannah's trying. She's better than I am. We're trying to get a few plants going. I would not say I have a green thumb. My mother used to say that she had the black thumb of death. But it's not easy to grow plants in Arizona. Like, the sun will just bake anything that you try to plant. So maybe she was better with plants than she thought. But it's just, the desert is going to get you every time. Let's just say that. Let's just say that. Okay. Looks like we have a little bit of a lighter crowd today at the start of the lecture. That's okay. You can come back. These videos are posted to Twitch. I also put them on YouTube, so you can see them in either of those places. And you can catch up with this content, but it's best to be here live if you can. You can follow along with these handouts. So, I've taken every Monday off through July. Need it for the sanity. That sounds like an amazing idea. That's a really great idea. Take a 3-day weekend every weekend in July. I'm a fan of that. Well done, Phil. Yeah, I think we all need a little bit of some outdoor time, especially nowadays, to keep it all together. So we are talking about state space. State space is a way to mathematically represent a dynamic system. And one of the advantages of this representation is that it's great for computer simulation. It's very efficient for that. So today we're going to show how once we have a state space model, we can go to MATLAB and run some simulations. Before we get to that, though, there's one more piece of state space that we need to cover, and that is the output equation. So before I tell you what the output equation is, I'm going to give you some motivation for why the output equation exists. So I wrote a little paragraph here. Often, we're not interested in recording the dynamics of every state of a system. So for example, systems might be of a very high order and thus require many state variables. Remember that the order of a system, so like the order of the differential equation that describes the system, we generally set that equal to a variable n. So n could be 100. We could have a 100th order system. Well, the order of a system is also equal to the number of states. So in real life, you might be modeling the dynamics of a system and find that it has very, very many states. But we may only want to save data from a couple of these states. Or maybe the data that we're interested in is a mathematical function of a couple states. Like, for example, we may need to add some states together to get the quantity that we want. So the limited number of states or combination of states that we want to actually record, we call these outputs. And the purpose of the output equation is to extract this data from the overall state space model. Now, I made 3 little examples down here to give you an idea of what these outputs are. So say we model, let's look at the first one. We model the lateral vibrations of a skyscraper. And I showed you this. One way to model a skyscraper is imagining it as a bunch of spring mass systems connected together, right on top of each other. And let's say we're modeling this skyscraper and it has 200 states, because you need 2 states for every floor at the least. And these states model the position and velocity of each floor. But let's say I only want to know how much the top floor is moving, because that floor is probably moving the most in the building. If you've ever stood at the top of a very tall skyscraper, it is a little unsettling, but if you put your head right on the window and look down towards the sidewalk, that floor is moving, my friend. Maybe you didn't want to know that. But let's say I only want to know how much that top floor is moving. Okay, in this case, my system output is the movement of the top floor. So even though this skyscraper, I describe it with a model that has 200 states, ultimately I'm only interested in one of those states, the movement of the top floor. Okay, that's an example of an output. Let's do the second example. Maybe I have a circuit with many loops, many inductors, and many capacitors. But I'm only interested in knowing the voltage drop across a particular capacitor in the circuit. So the voltage drop across this particular capacitor could be my system output. For a circuit, the number of states is equal to the number of capacitors plus the number of inductors. So if you see a circuit, you can just count up the number of capacitors, number of inductors. That's the order of the system. But we might only be interested in one of those. So if that's the case, we call that our output. Okay, one more example. This is for all you car mechanics, you car people out there. Let's say I have a model for the dynamics of a car. To model a car, there's varying levels of complexity you can go. but you can potentially have many states that describe the complicated body motions. But let's say for a particular problem, my outputs of interest are the forces in each of the shock absorbers at each tire. So let's say I'm interested in each tire. There's 4 tires, so I have 4 outputs, and the forces, those outputs are the forces in each shock absorber. All right. So outputs are information related to a limited number of states in our model. It's kind of like taking a magnifying glass to your system and saying, I just want to focus on this one part. So let's give the mathematical definition of this output equation. So given a state equation, this is the state equation. The output equation is going to be y of t, and this is bold-faced because it's a vector. You could have more than one output, and it's a vector because I stack each output on top of each other. So the output vector, y of t, is equal to a C matrix times z of t. Z is our state vector. And then we have plus a D matrix times our input vector, U. So y of t is the output vector. This output vector, if we have m outputs, the vector is going to be m by 1. We'll just stack them right on top of each other. So let's restate that information in a table. So when I type out this input vector y, I do boldface to represent a vector. And a lot of engineering textbooks, engineering papers do the same thing. They just do boldface. But when I write it by hand, I just put a line under it to indicate a vector. If you don't like doing it that way, you could do it another way. Some people like to write like an arrow on top. But I think those people are weird, so I don't do it. I just put a line underneath. Okay, the name, like I said, it's the output vector, and the dimension of that vector is m by 1. These C and D matrices, well, I don't do anything special with them when I write them by hand. So they just look the same. But this C matrix is called the output matrix. And this D matrix, it has a fancy name. The direct transmission matrix. Now I have these entries over here. I want to figure out the dimension of these matrices, but we're going to do it right down here. I'm going to have you figure it out. We're going to test your knowledge with a little bit of review too, because I'm going to ask you what size are the A, B, C, and D matrices if our state vector is n by 1, if our input vector is r by 1, and if our output vector is m by 1. Do you remember how to figure out these sizes? First, I'll put the state equation. I'll put the output equation over here. The way I like to do this is I label the size of each of the vectors first, which we We know that in advance. It's given in the problem statement. All right, let's see who's awake out there. First, a little review. Given these matrix equations, what size is the A matrix? This is your bravery test. Very good, Aaron. N by N. Remember, for those of you who weren't here, you can only multiply matrices if these interior dimensions are the same. And the final product, the size, once you've multiplied them together, is these outside dimensions. So this A times Z will be an n by 1 vector. And that's good because we need this to match what's on the left-hand side. Okay. Very good. What size is the B matrix? That guy right there. That's called our control influence matrix. Good. Aaron's on a roll. Okay. But what about the C matrix? Surely this is going to trip you up. Your perfect streak is going to be ruined with this one right here. Nope, you got it. Okay. Are you going to go 4 for 4? What about D? I think you're an expert at this point. I can't trick you. Not N by R. What does the... Well, remember, this equation is saying that in the end, the result is going to be M by 1. So if you add vectors together, they have to be the same size. Good. So this guy has to be M by R. So very close, Aaron. I'm impressed with the job you did. So both of these on the right-hand side are M by 1 vectors. And they match that quantity over there. So mathematically, we're all good. Okay, so we'll fill these dimensions in the table. All right, the C matrix was M by N, and the D matrix was M by R. Now, I think the best way to get familiar with this stuff is do a bunch of examples, and that is exactly what we're going to do on the next page. We're going to reacquaint ourselves with an old friend, the spring mass oscillator. So it looks like this. You have like some fixed surface. You have a mass, and it's connected to that fixed surface with a spring and like a damper. And let's say the mass was originally right here, but I pulled it to the right a distance x. So that's where the x variable comes from. Let's say the spring has a stiffness k, and this damping coefficient is c. And let's say we can apply some other external force. Maybe you're just pushing on it with your hand. And that's f of t. So if you apply Newton's laws to this, you come up with this differential equation. The mass times the acceleration is equal to the sum of forces. So I want to put this in state space form, and then we're going to define some output equations for this system. So the standard state definitions, I would say, you guys practice this with the last homework. I'll call my first state, put a t vector, the position, x of t. For mechanical systems, it's common to define your first state as like a position. And we'll call our second state the velocity. So that's always the first step, making a state space model. You introduce your state definitions. And then the next step is you take the first derivative of each state. And these first order equations, these are called your state equations. So the first derivative of that first state, that's just x dot. But I want to write these in terms of my other states. So x dot is the same as z2. And then z2 dot is x double dot, which is the acceleration. Well, let's go back up here to this equation to figure out exactly what that is. So x dot of t would be minus c over m, because I had to divide by m to isolate that acceleration by itself. And that force, I had to divide by m as well. Don't forget to divide everything through. I often forget to divide the force by m, so I have to like remind myself. So that is like homework 5. Are you talking about the state space or the... What was homework 5? My memory is foggy on that one. It's like problem number 5 in homework 7. Oh, I see. I see what you mean. Problem number 5, homework 7. Scroll down a little bit. Yes. Now, but this one, we'll get to this later. This is actually a model that I made for a washing machine. You know how a washing machine, sometimes it can get a little imbalanced and you hear it like thumping around once it gets on the spin cycle? Well, that happens because there's a little imbalance in the rotating mass in there, and that creates like a sinusoidal force. And that force, I think I made it this term, F. And if you ever open up your washing machine, you're going to see a collection of springs in there. And that attaches to the drum. And they also have at least one damper in there too. Sometimes it's on the top, sometimes it's on the bottom. And then they put a big block mass on top of your drum to make it a little heavier. And that's what I put this big M for. But yeah, a washing machine is like a spring mass system. And when they try to think of ways to prevent your washing machine from vibrating so much, they make a model like this, and they decide what the values of the springs, how stiff they should be, how heavy should the mass be, what should the damping values be, to try to reduce those vibrations. It's pretty cool. Maybe we'll work on that problem. Okay. So we'll write this acceleration out in terms of the states. And I'll just leave this variable as f. Sometimes we write that input variable as u. We'll call it like a control input, some external input. I'll just leave it as f this time though. All right, we're ready to put this in matrix form. So we go z1, z2, the first order derivatives. And if you like, I think I mentioned this before, you don't have to write these as z1, z2. You could also write them as x dot and x double dot. You could leave it in terms of those other variables. But I'm just going to do z1, z2 because I already started down this path. Okay. So we know that the A matrix should be 2 by 2 because I have two states. The A matrix is always square. Same number of rows and columns. We have one control input, but two states. So the B matrix is 2 by 1. It's like a tall matrix. And then I have this. And if I'm really thorough, I should mention that these are all a function of time. That's what the parentheses t means. Okay. So the top row is for our first state equation. So it's 0 times z1 plus 1 times z2 plus 0 times f of t. And then z2 dot is minus k over m times z1 minus c over m times z2 plus 1 over m times f of t. So this is our A matrix. That's our B matrix. So now we're going to run through, I think, 5 combinations of different possible output equations for this system. The first one is, let's say our output of interest is the position of the mass, which is x of t. Well, in terms of our states, that's our first state, z1. So what I want to do is write out our output equation in that formal way that I defined on the previous page with the using the C matrix and the D matrix. So, okay, here we have one output, so M equals 1. We know that our C matrix should be M by N. And for this problem, N equals 2 because we have two states. Our D matrix is M by R. R is our number of inputs, which is just 1. So our C matrix should be 1 by 2. D matrix should be 1 by 1. So I'm going to start writing this out. So the y, our output is our C matrix times our state vector plus our D matrix times our input vector. And this C matrix is a 1 by 2, so it's got 1 row, 2 columns. All right, let's see how awake you guys are. What should the C matrix be? Okay, let's try that out. What if I make it 0, 1? Let's multiply this out. So this will say y is equal to 0 times z1 plus 1 times z2. And then we'd be left with z2. But we want to get z1. So you got to switch it. If my pen will cooperate. But if I do 1, 0, then it'll be 1 times z1 plus 0 times z2. And because this is just equal to z1, it doesn't directly depend on f of t. So our D matrix is 0. Okay, let's do another one. We'll just keep doing some examples. Let's say if our output was instead the velocity. So it's z2 of t. So in this case, the number of outputs is 1. So m equals 1. The number of states hasn't changed. It's from the same model. N equals 2. R equals 1. Okay. So in this case, now, Aaron, you're good as gold on this one. Because for this one, we actually want Z2. So we just switch it. 0, 1. The way you test these, you just multiply out the matrices. And you'll see if I multiply that top one all the way out, it would just give me back Z1 of t. If I multiplied this one out, it would give me Z2 of t. So sometimes if you're stuck, you can just try something, multiply it all out, see if it gives you back what you want. All right, let's try 2 outputs. Sometimes you might want to recover more than one. So let's say we want the position and the velocity. So our output vector is going to be z1, which is x, on top of z2, which is x dot. So in this case, oh, that's the weirdest m. Okay, m is 2, because I have 2 outputs. And N and R haven't changed. We're only changing the outputs here. So maybe I'll stop rewriting this N and R because they're not going to change for any of these. So now, y of t is a vector. That's why I put a line under it. And that's why I bold-faced it here. So our C matrix is, the dimension is m by n. So M is 2, N is 2. So this is going to be a 2 by 2 C matrix multiplied with my state vector. The D matrix is M by R, just 2 by 1, times f of t. Now, if you look at this, this example is the combination of the previous two examples. So I could just stack the result from the first example on top of the result from the second example. Because the first one returned Z1, which is what I want, and the second one returned Z2. So I just stack those two. Can you label the matrix dimension just for future reference? You mean like this? 2 by 2, or just like the general, like these ones up here. This one's 1 by 1, 1 by 2. So it's just row as the first entry, column as the second entry. 1 by 2, 1 by 1. Like M by R, N by N. Yep. That's what this guy is up here. So the C and D matrices, they're always going to be M by N and M by R. That's not going to change. No, you're good. You stepped away. Well, welcome back, Phil. Welcome back. Okay, so we've done a couple position and velocity examples. This one's going to be a little trickier. Let's say I have this spring mass system, and I'm interested in how much force is the spring and the damper putting on the mass. So in other words, I got my mass here. Let's say I move this a distance x to the right, so that's my position. Well, it's going to stretch this spring. It's going to stretch this damper at some rate, and these are going to, the spring is going to want to pull back on this mass. So it's going to create a force to the left. The magnitude of this force is going to be minus k times the distance it was stretched. Does that make sense? I pulled this mass a distance x to the right. Well, that stretches the spring a distance x. The force by Hooke's law is the distance times the spring constant. And I call it negative because x is defined positive to the right. Okay. The force from the damper is proportional to the velocity. So how quickly am I pulling it to the right? So let's say I want this combined force. So I'm saying my output is going to be minus k times x of t minus c times x dot of t. So I'm combining those two forces together. And if I write it in terms of the states, that's minus k times z1 of t minus c times z2 of t. And maybe just as a note on the side, you know, m equals 1. That's my number of outputs. N equals 2. That's my number of states. And R equals 1. It's my number of inputs. All right, let's start writing this out. So my output, y of t, my C matrix is going to be m by n, so 1 by 2, z1, z2, plus my D matrix, which is 1 by 1 in this case, times my input vector. All right. What's the C matrix? Are you still there, Aaron? Yes! Wait. Okay, if I do -1, -1. Let's do a test. And this D matrix is going to be 0. If I multiply this out, it's going to be -1 times Z1, -1 times Z2, plus 0 times f of t. But this won't be the force. Ah, okay. Good. I need minus k times z1 minus c times z2. Brilliant. We got it. All is forgiven. And do you think we're done with these examples yet? No, because I have 2 more for the spring mass system. You thought you were in the clear. Not yet, my friends. Because I'm going to trick you even more. What if I want my output to be the acceleration of the mass? So that's x double dot of t. What do you do in this case? Because my first state is the position, my other state is the velocity. I don't have a state for x double dot. So am I up a creek without a paddle, as they say? Or is there some way out? This is always a little tricky the first time you see it. So, even though this is x double dot and we don't have a state for x double dot, it turns out x double dot is a function of our states. I will show you. Because, look at this right here. Z2 dot was x double dot, and that's equal to minus c over m times z2 minus k over m times z1 plus f of t over m. So I know that this is going to be minus c over m. So it comes from our equation of motion. Plus f over m. And then in terms of our states, z2 plus 1 over m f. So now we can write this as a matrix equation. Let's throw those t's in there for good measure. All right, so let's just fill this in. It's minus k over m times z1 minus c over m times z2 plus 1 over m times f of t. So this was the first example so far where our D matrix was non-zero. So maybe I'll make a note here. The only time you have a non-zero D matrix is if your output depends directly on your control input. Is if the output vector depends directly on the input vector in some way. So in this case, acceleration is directly dependent on force. If I push you, you immediately start accelerating. And then when you accelerate, that creates velocity. Velocity creates change in position. And so on and so forth. Oh man, this example is going to test you to the limits. Because let's say that I want 4 outputs. I want the position, I want the velocity, I want the acceleration of the mass, and I also want the force from the spring and the damper. So what if my output vector is everything from all the prior examples? I want it all. Okay. Well, let's just write it out first. So I want position. I want velocity. I want acceleration. I want the force in the spring and the damper. What was that? Minus k x of t minus c x dot of t. So I'm saying this is my output vector. So there's 4 of them. So m equals 4. So you write this in terms of your states. Z1 of t, Z2 of t, x double dot, we just did that. minus k over m z1 of t minus c over m z2 of t. I haven't put this in the full matrix form yet. I just wanted to like write out what each element is equal to. So minus k z1 of t minus c z2 of t. Whew! All right, are you ready? What size is my C matrix? Maybe I'll give you guys a minute or two. Try to write this out on your own, on a sheet of paper, before I even do it. And then I'll do it after you. You can check your answer. I'm going to go fill up my water bottle. Give you an opportunity to grind away on that for a second. Are you making progress? Let's see how you're doing. So because the C matrix is M by N, number of outputs by number of states, it has to be 4 by 2. Which is a little strange because usually the number of outputs is less than the number of states, but in this weird example it's more. I have 4 outputs but only 2 states. Two columns, 4 rows. And then the D matrix is 4 by 1. Okay. I'll start filling it in. The first state is it's just equal to Z1, our first output is just equal to our first state. So 1, 0, 0 all the way across. Velocity 0, 1, 0. The acceleration minus k over m times our first state minus c over m times our second state plus 1 over m times f. And then our last output, the force, is minus k times z1 minus c times z2 plus 0 times f of t. Did you get it? And if you're ever like, oh, I don't know if this is right, just multiply it out over here. And if I multiply this out, I'm pretty sure, if not absolutely certain, that I'm going to get that vector up above, which is what I wanted. So it's not too bad. Okay, now we're going to go to the big leagues. We did 5 or 6 examples with a spring mass system. Now we're ready for an aircraft. We are ready to make a state space model for an aircraft. You can do it. Whoo! We got a lot of equations here. So I showed you this before in one of the previous lectures, but this describes, so we have 3 first order equations, and it's describing the translational speed relative to the wind of this aircraft in 3 directions. So, actually, the best way to define it is using this right here. So, u of t is the longitudinal velocity. So that's like how fast you go relative to the wind, like looking out the windshield of the aircraft. Lateral velocity would be how fast am I going if I'm looking out this right wing. And the normal velocity is how quickly we're heading down. Hopefully not too fast. Hopefully we're staying airborne. We're going to have 5 control inputs to this system. We have the aerodynamic forces in the longitudinal, lateral, and normal directions. So those aerodynamic forces are capital X, capital Y, capital Z. Other inputs for this system are going to be the pitch angle, theta of t, and the roll angle, phi of t. So we have some forces, and we're assuming these other angles to also be control inputs, controlled by the autopilot or something. The 2 outputs that we're interested in, I want the normal velocity, which is just one of the states. And the second output I want is the gravitational force that's normal to the aircraft. And it's this expression right here. Don't worry too much about the math. We're just trying to write this in state space form, given these equations already. So, first, we're going to start by writing. Actually, you know what? Maybe we'll just skip. No, let's do the whole thing. Let's do the whole thing, guys. We're going to do the state equation and the output equation. So, we're going to try to do this in one go. So my state derivative vector, z dot, that is going to be u dot v dot. Maybe I should spread these out a little bit so I have some space. U dot v dot w dot. Ooh, let's define how big all of these matrices are going to be. So my state vector, this is 3 by 1, which in the variables we've been defining, that's n by 1. So n is 3. Our input vector, we have 5 of them, 5 by 1. And the number of inputs, we've been calling that r. So this is r by 1, where r is 5. And finally, our output vector is 2 by 1, which is m by 1. So m equals 2. I know my A matrix is going to be n by n. So it's going to be 5 by 5. So it's cool because these are things that you can know in advance. It helps you to check your work. B is going to be n by r. So it's going to be... Oh, wait. I messed up. N is only 3. So the A matrix is 3 by 3. I'm sorry. B is n by r. This is going to be 3 by 5. C is going to be m by n. So it's going to be 2 by 3. The D matrix is going to be m by r. 2 by 5. All right. So this will be a little interesting with the space here. Wait, maybe I should just put it down here. Yeah, that looks better. So this is going to be a 3 by 3 matrix times my states, U, V, W. I'm going to move this down a little bit. I'll try to partition these out in advance to give myself some space. This is a big equation though. I hope that all the entries fit in there. Okay, so this is our A matrix. It's 3 by 3. It's called our system matrix or our plant. And then we have plus our B matrix, which we know to be 3 by 5. Good gravy. Let's see if that works. One, so 3 rows, and then I need 5 columns. 1, 2. So they're not very even columns. Okay. And then I have 5 different inputs. So I have to put my input vector over here. It's a 5 by 1. Who'd have thought we were doing a state space representation for an aircraft today? Did you get out of bed this morning and think, heck, that's what I'm doing today? Okay. So we kind of made a template for us to fill in using the equations up above. And we're going to do it one by one. We have 3 equations. The first one we're going to deal with is this U dot equation, which looks really, really tiny right now. This is the struggle. Okay, we'll zoom in on it for a little bit here. So this is going to depend on W and V. Those are two of our states. X is one of our inputs, and theta is another one of our inputs. All these other things are just constants. So those constants are what's going to actually be used to fill up our matrix. Now, something to notice, our state is u dot by itself. So we have to divide by m in these equations. So these m terms are not going to show up. Oh, except when I divide left and right hand sides by m, x is going to be divided by m. Okay, let's fill this in. Let's fill this in. So I'm going to have u dot. It doesn't depend on u of t. It does depend on v. It's r naught times v of t. And it's q naught times w of t, which is our third state. Okay. Now we're moving over to our B matrix. So it does depend on x of t. It's 1 over m times x of t. It doesn't depend on y or z, which are our next two inputs. It does depend on theta. So the term multiplying theta, you probably can't see it. You'll have to take my word for it. But it's g cosine of theta naught. And that'll be hard to squeeze in here. G cosine theta naught. Okay, I guess we got it in there. And it doesn't depend on phi of t, so I put a 0 there. All right, 1 row down, 2 to go. Let's look at this second equation, v dot. First, we'll zoom in on it and just kind of talk about it. Once again, we're going to divide by m. So the m is going to cancel here. I'm going to have y of t divided by m, but that's going to cancel here. Okay, great. In terms of the other states, it depends on u and w, but it doesn't depend on v. So maybe I'll just like put a box. It does depend on y of t. It depends on phi of t and theta of t. All right. We can do this. Minus. Oh, you know what though? I'm noticing something. In this first equation, it should have been a minus q naught. Because I have minus q naught times wt plus r naught times v of t. So that r naught should be positive, but the q naught should be minus. Okay. Oh. And that means this term, this g, this should have been a minus. Minus g cosine theta naught. Okay. Okay, moving on to the second one. We're going to have r naught times u, but minus r naught times u. 0 times v plus P naught times W. Nothing times x of t. 1 over m times y of t. Nothing times z of t. Theta is our next state. So I'm going to have minus g sine phi naught sine theta naught. That's going to be hard to fit in there. Minus g. Maybe I'll start towards the top of this box. Minus g sine theta naught. Times sine phi of naught. Oh my goodness. But I couldn't fit that all on one line, so we're just going to write it like that. Okay. So that's multiplying with theta, and then we have another term multiplying with phi, but I'm going to have to go up here to see what it is. We're going to have positive g cosine phi times cosine theta. Okay, so it's kind of like the last term we wrote, but it's going to be positive and it's going to be cosines instead of sines. So I'll just say it's g cosine theta naught times sine phi naught. Oh, that's not too bad. Are you guys following along okay? I know we're bouncing back and forth. If you can get the handout in front of you, it'll be a little easier if you're trying to follow along. Okay, we got this last row. Let's try to go through this. Power through it. Okay, z divided by m. That cancels. Okay. All right, so we'll start with this A matrix. So it doesn't depend on W, so I'll put a 0 there in advance. It's going to be positive Q naught times U minus P naught times V. Oh my goodness, we finished the A matrix. Goodness gracious. Okay, this is going to be 0, 0, 1 over m. Do you notice little patterns in these matrices? That's often the case when you're modeling physical real-life systems. These patterns emerge. Okay, so I'm looking at what's going to multiply theta and phi. For theta, minus g cosine sine. Okay. I believe that's what it was. Minus g cosine phi naught times sine theta naught. And then there will be a similar term in this bottom right hand corner. Let's scale out a little bit here. It's going to be minus sine phi naught cosine theta naught. Okay. Guys, that's it. The B matrix is done. I'll zoom back in a little so you can see that. B matrix, 3 by 5. Okay, that took longer than I thought it would. But nonetheless, it is beneficial. Let's do our outputs. Hopefully we can slam through those really quick because I want to get to some MATLAB stuff. Okay, Olivia says second row, fifth column should be cosine phi. Okay, second row, fifth column. Oh, thank you very much. You're absolutely right. Okay. She's talking about this right here. Thank you very much for catching that. Yeah, this row is sine, sine, cosine, cosine, and then they get switched. Cosine, sine, sine, cosine. Thank you, thank you, thank you. Let's do our output. Y is going to be our C matrix, 2 by 3. Let's just block that out. Times our state vector. And notice this time I'm not writing my states as Z1, Z2, Z3. I'm just using these variables. You're always welcome to do that. Okay. D matrix, 2 by 5. Oh, maybe I have to scoot this down a little bit. Just a little bit. Oh, I'm gonna copy this. I know you don't have the luxury of copying unless you're also working on a tablet or something. But that's okay. Okay, so we said the C matrix is 2 by 3. The D matrix is 2 by 5. 1, 2, 3. Okay. That's what I like to do first. You're going to know what size the matrices are, so why not block them out? It's a good way to check your work. Okay. Now our first output is W, so the normal velocity. Fortunately, that's going to be really easy because W is our normal velocity, so 0, 0, 1, and 0 on everything else. Boom. Easy. Our second output is the gravitational force normal to the aircraft. So I'm going to have to zoom in here to figure out what the heck that is. mg. Okay, so it's going to have one term multiplying phi and another term multiplying theta. So theta is going to come first, so we're going to put that. Minus mg cosine phi sine theta. Let's see if I can remember that. Okay. Minus mg cosine phi naught times sine theta naught. Did I remember that right? We'll check in a second. And the rest of these are 0, by the way, because it doesn't depend on X, Y, or Z. All right, let's look at the other one. mg cosine phi sine theta. Okay, that looks right. So this one's going to be switched a little bit. Minus mg sine phi cosine theta. Okay. Minus mg sine phi times cosine theta. Okay. I'm going to zoom out a little bit. Oh, we got to fill in the C matrix, though. It'll be 0, 0, 0 for that entry. Okay. That is a state space model complete with an output equation for an aircraft. Now you can say you've done a state space model for a 747 or something. Okay. We've done a lot of practice making state space matrices, output equation matrices. These are going to come in handy, these matrices, when we do simulations in MATLAB. So that's what the remaining time is going to be about. How can you take these matrices, put them into MATLAB, and do some simulations? But I think we should take like a 3-minute break because we've been grinding through these matrix equations. So I have a time of 3:27 Eastern. At 3:30 Eastern, we're going to resume and talk about some MATLAB. So if you have your computer handy, it'll be nice to follow along the coding with me. We'll just run through some basic, useful commands. All right, we'll be right back, everybody. I have an interesting little poof thing going on with my hair right now. That's pretty sweet. All right, you got your MATLAB ready? We're going to take all this state space knowledge, throw it into MATLAB. Okay. Okay. The first thing we're going to learn how to do is create a state space object in MATLAB. So something that MATLAB will recognize as a state space model. Okay. So with these examples, we're going to just use that spring mass model. Assuming the same states. Let's assume the outputs are the position and the velocity of the mass. So I'll quickly write down our state space model. This time, instead of Z1 and Z2, I'm just using X and X dot. So this is 0, 1, minus K over M, minus C over M, X dot. So that's our A matrix. Our B matrix is 0, 1 over M times our force. And then our output vector, if we want it to be the position and the velocity, I think it'll be just like our third example up at the beginning. So 0, 0, f of t. So we have A, B, C, and D. So I'm going to define these matrices in MATLAB, and then I'm going to make a state space object. So you do it with the SS command. So it's SS of A, B, C, D. Let's go into MATLAB to do that. Okay. So I said M was 1 kilogram. Our damping coefficient C 0.1 newtons per meter per second. K is 10 newtons per meter. Now I'm going to make my A matrix 0, 1. Then I go to the next row. Minus K divided by M. Minus C divided by M. And that's the A matrix. B is 0. Then we go to the next row. 1 divided by M. C is 1, 0, 0, 1. But you know what? I'm going to show you a trick. So this makes a diagonal matrix with 1s along the diagonal entry. That's also called an identity matrix. So a quick way to make an identity matrix in MATLAB is to do I. I know it's written like I, like your eyeball, but it makes an identity matrix. And this entry here, it's a 2. It tells you how big that matrix is. So an identity matrix is always square. So I'm just saying this is a 2-dimensional identity matrix. So it's 2 by 2. So if I run this, I'll just evaluate that. You'll see in my MATLAB, that command makes 1001. That's a little trick. Tuck it away. All right, and then D is 0 on top of 0. You know what? I could show you another trick though. You can use the command zeros and you put in the dimension of that matrix. So this will make a 2x1 matrix filled with zeros. If I evaluate this, you'll see. That's what that does. So I'll show you some little tricks along the way. So if I was coding on my own, I might do it this way. Actually, it might be faster to just write 0, 0 here. I usually pick the faster option. All right, so we have A, B, C, and D. So I'm going to say my system is state space A, B, C, D. Let's run this code. I'll save it in class 6/15/2020. All right, let's see what happened. My system. So it tells me, oh, okay, you gave me a continuous time state space model with this A matrix, this B matrix, this C matrix, that D matrix. And we're done here. That's how you make a state space object. And now we're going to show you some cool stuff that you can do with it. All right, the first thing we're going to do, let's calculate the homogeneous solution of a state space model. And the command we're going to use for this is the initial command. It's called initial because the homogeneous solution is how the dynamics of a system respond to non-zero initial conditions. So what we're going to do, we're going to imagine that we pull this spring mass system 1 meter to the right, and then we have the velocity equal to 0. So we just pull it to the right, we hold it still, and that's our initial condition. And then we let go of it, and we don't apply any other external forcing to the system. So the right-hand side of the equation will be 0, and it'll be a homogeneous response. So if you use the initial command, let's walk it through really quick. The first argument is your state space object. So we already made this. This next argument is the initial conditions. So we're going to call Z naught. Why am I doing that? I'll just call it Z naught. It's going to be 1, 0. And then this T final is, well, the final time of your simulation. How long do you want this to run? What I like to do for final time of simulation is start with the settling time, because by then you know that the homogeneous solution should have decayed 98% of the way to where it's finally going to go. So I'm going to set it equal to the settling time of the system. Now, there's one other thing I wanted to talk about, which is calculating the settling time in MATLAB with one line of code automatically. because this is kind of cute, kind of cool. We know that the settling time is 4 times the time constant, tau. And what is tau? It's -1 over the real part of the roots. But it's the real part of the slowest root. Because we might have like a system with many roots. And how do you define the settling time of the overall system? Well, you define it based on the slowest root. So I'll make a note here. It'll be the slowest root in there. The slowest root is the one, assuming that all of the roots are stable. That would mean that all of the roots have a negative real part. The slowest root has the smallest real part. It'll be negative, but it'll be the smallest. Okay, so this is what I do in MATLAB to calculate the settling time of any order system. I start by taking the eigenvalues of the A matrix, because remember, the eigenvalues of your A matrix are the same as your system roots. Okay? So if you take the eigenvalues of A, it gives you all of your system roots. Now the settling time is based on the real part of those roots. If you use the command real in MATLAB, it'll return the real parts of the eigenvalues. Okay, so let's say you had 5 roots. Some of them had imaginary parts, whatever. When you take real, this will just give you a vector of 5 real parts. And if the system's stable, all of these numbers are going to be negative. So I want the root that's smallest, because if it has a small negative real part, then it's slow. But how do you get the smallest of negative numbers? Because if you use like the minimum command, it'll actually find the most negative root. And that's not what you want, because that would actually be the fastest root. So what I do is I take the absolute value of all of the real ones. So now they become positive numbers. And now the slowest root will be the minimum of these. If you take it in steps, starting from the eigenvalues, it makes sense. So tau is going to be equal to 1 divided by this. Usually tau is -1 over the real part of the slowest root, but because I took the absolute value of all of those roots, this is already a positive number, so I don't need that negative sign out in front. So maybe even to reiterate that, I'll say it's positive. And then to get the settling time, you just multiply that by 4. Does that make sense? It might be a little confusing at first, but I think if you think about it a little bit, you won't be confused at all. Okay, so we're going to calculate the settling time in this way, and that's what we'll plug in for that final value there. All right, let's go to MATLAB. Okay, simulating homogeneous response. So this is the syntax: y, t, z, initial. I plug in my state space system. I give it my initial conditions, and then I give my final time. So let's put our initial conditions. It'll be 1, 0. And okay, let's do this. Tau, I take the eigenvalues of my A matrix. I find the real parts. I take the absolute value of all the real parts. So now they should be positive numbers. And I find the smallest one. And that'll be the absolute value of the real part of the slowest route. And then if I divide that whole thing by 1, that's my time constant. And then my settling time is 4 times tau. Isn't that cool? And it doesn't matter how big your A matrix is. This could be a 200th order system. This one line of code will break all of that down, find the slowest route. That's one of the cool things about MATLAB. It does all this work for you. Okay, so we have our system defined, we have our initial conditions defined, we have our final time defined. Okay, and then what this gives us back, the stuff on the left-hand side is what the function gives us. It gives us our outputs, y. It gives us our time vector, t. And it gives us our states as well. Okay, so I'm going to plot the results. Plot time. I'm going to plot my outputs. I'm going to make the line width 2 to make it a little beefier. I'm going to turn on my grid. I'm going to label my x-axis. Time in seconds. I'm going to make a legend. Because my first output was the position. First output. My other one was the velocity. Second output. Let's run this. Uh-oh. I got an error. Undefined function or variable t final in line 21. Ah. We never defined t final. Let's make it equal to the settling time. And let's try again. Now it works. Look at our position. We pulled that mass 1 unit to the right, we released it, and then it goes just like we expect. It oscillates back and forth and decays. And because I automatically defined us to run to the settling time, it picked how long, well, I picked how long the time vector should be. And there it goes. So just like that, that's how we do the initial condition response. But I have 2 more things in MATLAB I want to show you. All right, maybe I'll, just so when people come back to this, output vector, time vector, state vector. All right, so that's the homogeneous response. Just non-zero initial conditions and let the system go and do what it will. What if we want to do the step response? You guessed it. It's the step command. It's popular enough to have its own command in MATLAB. Now I made a note here. The step response implies that all initial conditions are set equal to 0. And that's why, like in the initial condition one, they had an entry in here for initial conditions, but we don't have that here because it's implied to be 0. Here's our state space object. You specify the final time. This gives you back your outputs. And then it also gives you the time vector that it created. Oh, I have something else down here. Ooh. I'll ask that question after. Okay, let's go to MATLAB. Okay, so this part, getting the step response. Okay, in this case, YT is step of my system, and then at the T final. And I'm going to just take this same piece of code for generating the figure. I'm going to copy it down here. But you know what? I'm going to put a title on it this time. We'll call it the unit step response of spring mass system. And I'm just going to run this excerpt of code. Boom. So the blue is the position. So I push this mass to the right and it oscillates, but eventually it settles at some non-zero position. The velocity, it oscillates, but it goes down to 0 eventually. So this mass is going to be sitting still at some non-zero position because I'm applying a force. So easy as that, it gives us the complete solution, homogeneous plus particular, when you apply a step input. Now, so step, this says f of t equals 1. Okay, but what about this question? What if I want to get the step response with a step magnitude other than 1? So what if I want like f of t equals 10 or something like that? So for example, now we know something about linear systems that lets us answer this pretty easily. I let you know about two properties. One of them is the scaling property. The other one is the superposition property. And they're both pretty similar. So how could I use the step command to get the response of my system where I increase the input by 10 times the original amplitude? Any brave answers out there? If I take a force like this and I put it through a linear system, it gives us some like output. Let's call it x of t. If I put 10 times into the same system, what comes out? Oh, yes. Aaron, you are correct. Just multiply it by 10. Or, no. You don't multiply my system by 10. Because if you did that, your A matrix, your B matrix, your C matrix, your D matrix would be 10 times. And then it wouldn't be the same system anymore. You know what I mean? You would have made it 10 times the same system. So we preserve the original model and differential equation or whatever. But if we change the input by 10 times, it just means the output increases by 10 times. So, if I want to increase the amplitude of step by 10 times, then, well, you could do this because it increases. Wait. No, I don't want to do that. I don't think I want to do that. I think all you do is you say y new is 10 times. So it's saying my output from before, I multiply it by 10, and that's the new one. So let's do y new. And let's also plot t y. And then I think I have to do this because it's going to give me more. So I'll say this like new velocity new. Let's try this. Yeah. So our new one, it's going to be 10 times higher up here. But notice the velocity, it's still going to go back to 0 eventually. But it has like 10 times the amplitude of oscillation. So the answer is you take whatever you got from before and you scale it by the appropriate amount. Okay. Let us, I know we're running short on time, but I want to show you this last command as well. This command is powerful. It can do it all. Calculating the response of a state-space model to an arbitrary set of inputs. So it doesn't have to be a step. It could be a sine. It could be like a random wonky signal. It could be anything. The way we do that, we use the lsim command. So to test out lsim, why don't we do a sinusoidal input? Let's say like f of t is, let's say it's like 20 sine 2 pi t. So this is a sinusoid with an amplitude of 20, and it has 1 cycle per second. And that's going to be our forcing function to the spring mass system. Okay, now this function works a little bit different because, well, it starts off the same. So you give it a state space model. You provide your own input vector. You provide your own time vector. And you also make up your own initial conditions. So you can have non-zero initial conditions, whatever you want them to be, and you can make your input whatever you want it to be. So you have all of this creative flexibility. So it's really cool. And then just like before, it gives you back your states, it gives you back your outputs, and it returns the same time vector that you made originally. Okay. Let's go to MATLAB. This should just take a couple more minutes. We started a little late today, so it's okay to go over a little bit. Okay, using LSIM to simulate the sinusoidal response. So here's the syntax: y, t, z. LSIM of my sys u t z naught. Okay, let's start with some easy ones. Let's say I want my initial conditions to just be 0, 0. So we'll start it at rest still. My sys, we already defined it. We need to define the input vector and the time vector. So I'll write out what our input vector is going to be. 20 times sine 2 times pi times t. But we have to make up this time vector. And I'm going to do something a little bit different when I make my time vector this time. I want it to start at 0, go by increments of dt up to the settling time. What's different is I haven't used this dt before, where I specify what the time step should be. So in other words, this is the interval of time between successive samples. So should this be a millisecond? Should this be a microsecond? Should it just be 1 second? So let's go back to the tablet real quick. And that's the question that I pose here. How small should I make the time step in my vector? Like, should it be a microsecond, millisecond, blah, 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 blah. Well, you want your graph to appear smooth. So if you want that to be the case, you should sample at least 10 times per oscillation cycle. Let me explain what I mean. Let's make some axes. So this is time. Let's call this axis x of t. And let's say in real life, the function is oscillating like this. And you know, everything in real life is continuous and smooth. But in MATLAB, I have to choose where I'm actually going to sample this. In other words, where am I going to calculate x of t? Because I can't do it at every single time. I have to pick some intervals. Actually, let's draw some intervals on here. First, I'm going to draw intervals that are way too slow. Let's say I sample at, so I'm going to try to evenly space these. Here we go. And I don't have to go the whole way, but if I sample it this time, I'm going to get this point, I'm going to get this point, I'm going to get this point, I'm going to get this point. So where I drew each of these tick marks, I'm seeing where the red line is at that tick mark. If I were to connect these lines, look at how nasty this signal is going to look. It's going to be this kind of like jaggedy looking thing, and it's not smooth at all. I'll even make that thicker so you can just tell. And we do not want, when we're simulating our system, we don't want it to look like this jagged saw edge kind of thing. So if you run a simulation and your response looks like that, like some monster fangs, well, that's telling you that your time step between samples is too big. It's too slow. You need to sample much faster. So a general rule of thumb that I like to use is this, that you should sample at least 10 times per oscillation cycle. So, you know, one cycle is going from peak to the other peak. So I think you should choose your sampling rate in such a way that you get at least 10 points in between there. I don't know if that was 10, 1, 2, 3. You know what I mean, though. If you do that, then you guarantee that your signal is going to look pretty smooth. Okay. How do you know how fast you have to sample? Like, if I just give you that rule for a general system, how do you know how fast it's going to be oscillating? We won't take up way too much time here. But for an underdamped system, you know the solution looks like this. Like a second order system. It has that homogeneous part. And then if you have you're going to have your particular part too. So this time we're giving a sinusoidal input. So the particular part is going to be a sinusoid, and I'll call it like it's going to have a sinusoidal part with some frequency and a cosine with some frequency. So what you should do, you should look at these frequencies. So omega is going to be different from omega d. What I would do, find the fastest frequency and then sample 10 times faster than that. So this is, in other words, this is saying, I know that the solution is going to be a superposition of some sinusoids. Some of them might be faster than others. But if my signal is going to be smooth, then I should be able to make even the fast parts of my signal smooth. So I have to sample many times, well, 10 times within each cycle of even the fastest parts. So I find the fastest, and I make the sampling frequency 10 times faster than that. This is relevant because in LSIM you have to pick your own time vector. So we're making it right here. So, okay, here's what I'm going to do. I chose the forcing function specifically so that the damped natural frequency would be the fastest. So I'm going to show you another trick to find the damped natural frequency, or the fastest damped natural frequency. So if you take the roots of your system, so the eigenvalues of your plant, what is the damped natural frequency? Well, that comes from the imaginary parts of the roots. So you take the imaginary, you just look at those. And then the damped natural frequency, remember, it's the imaginary component of each root. The bigger it is, the faster the root is. So if I take the maximum of the imaginary parts of my eigenvalues, that's going to be the fastest root in my system. So I'm going to say my sampling frequency is going to be, well, and this frequency right here is in radians per second. Why don't we just do that? I know that's the longest variable name in the world, but whatever. And then if I want to convert this into hertz, cycles per second, I take it in radians per second and I divide by 2 pi. And this is where we get to dt, the time between samples. The time between samples is 1 divided by your sampling frequency. So this guarantees in my time vector that this step is small enough that I sample 10 times per cycle. And it'll look pretty smooth. Okay, so we defined a time vector, we defined u, we defined z naught. Ooh, we are ready to simulate this system, and then I'm going to copy this code to get the plot. Let's run it. Oh no. This doesn't seem right. Two times pi times t. Settling time is 80 seconds. But this sine should have 1 cycle per second. What is going on here? That looks way too slow. I wonder if I have to, like, the input signal is undersampled. Use a sampling period smaller than 0.25. What was our sampling? Okay. Max of the imaginary of the eigenvalues. Let's look at this. What's the sampling frequency? 3 radians per second. Sampling frequency in hertz. Oh. Because I didn't follow my own rule. I said I was going to take 10 times of that. This is the frequency. And then I'm going to sample 10 times higher. So I forgot to follow my own rule. Okay, let's see what happens now. Okay, 10 times that. This should have 1 cycle per second. Let's just see what happens. That's better. Now if I zoom in here, well, that still doesn't look as smooth as I want. What do you say we go 30 times higher? So we'll get 30 points per oscillation cycle. That's a lot better. Oh, you know what it is? I think that this has a higher frequency. 2 times pi, yeah. This is higher frequency than the maxed damped natural frequency of this. Because that's 3.1. And then this one, the frequency of this is 2 pi. So really, I should have been using this as the highest. And that's why I had to go even higher to make this look smoother. Okay. Guys, that's what I wanted to show you today. I feel like we went 100 miles an hour the whole time today. We did a lot of matrix math, and then we did a lot of MATLAB, just like boom, 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 boom. But I hope that makes sense to you. I hope you've taken away some good stuff today. You guys are doing very well. I'm getting the first project ready. My plan is to have 2 projects in this course. So the first project, I'm going to assign it to you like any day now. And the projects will like combine topics from the stuff we've done so far. So you'll recruit all of your knowledge to do it. How are you guys feeling? You doing all right? Did you see the UB email today from the President Tripathi. It looks like the plan is to partially reopen UB in the fall. Do you guys see that? So some classes should be online. Some should be in person with like reduced seating capacity.
I said, empty your mind. Be formless, shapeless, like water.
What do you guys think about that?
Water into a cup. It becomes the cup. You put water into a bottle, it becomes the bottle. You put it in a teapot, it becomes the teapot. The water can flow, or it can crash. Be water, my friend.
All right, everybody. I think we're going to call it a day. Thanks for your time. Thanks for your attention. We'll see you tomorrow from 4 to 5 Eastern for office hours. Adios.